Swayam Prabha. Digital India. Educated India.
So now let's talk about heterogeneous reactions in bioprocesses. Now we have just discussed about the different types of fluid behaviors and under different conditions. So we now have some idea that the fermentation at high cell density do not continue to behave as Newtonian, but they can start deviating from ideality and behave like non-Newtonian fluids. Now this may further lead to heterogeneous reactions in bioprocesses. Now what does this mean? Now this can be involved in fermentations where there are either high cell densities or flocculation is happening, or there are immobilized cells structures where there can be mass transfer limitations. So now bioprocesses which involve, for example, solid phase, where microbial flocks or mycelial pellets might be getting formed, or in your wastewater treatment plants where biofilms are required, or like plant cell fermentations where plant cells tend to aggregate and they form small aggregate size. Then tissue engineering on 3D scaffolds where the tissue starts growing on a solid 3D structure, or immobilized systems like immobilized cells or immobilized enzymes where heterogeneous reactions can happen. Now let us take an example of immobilized systems and let us try to characterize the mass transfer process in these immobilized structures. Now rate of bioreaction we know in an immobilized system would be dependent on the rate of mass transfer outside or inside the solid catalyst for the substrate. Now if cells or enzymes, they do not spontaneously form clumps or attach to solid surface, they can be induced to do so by using immobilization techniques. Now many procedures for immobilization are available for artificial immobilization for cells and enzymes. Let us take an example as shown in the figure on the slide. You can see figure A where a gel particle has immobilized cells embedded in it, and the figure B shows a porous structure, a porous particle where the cells have settled in the pores, or the enzymes have settled in the inside the pores of this solid structure. Now in both these cases, the substrate has to diffuse in from the bulk liquid and reach the reaction center or the enzyme for the reaction to happen. Now let us assume, as shown on the picture here, that the substrate concentration in the bulk is denoted as CSB. So the path which it has to take to reach to the immobilized enzyme before the reaction can take place will involve step 1, which means movement from the bulk to the surface. Now this surface is nothing but the film. So as we had studied earlier, this is an immobilized enzyme suspended in a liquid. So there will be a solid liquid boundary. So this shows the boundary layer, the dotted line, and till the surface of the immobilized enzyme. So first it has to reach to from the bulk to the surface of the boundary layer, and then it has to cross the boundary layer and reach the surface of the enzyme, and from the surface it has to diffuse in to reach the enzyme. So this is nothing but a diagram of the path of the substrate to the reaction site. So as I said earlier, step 1, it is the transfer of the substrate from the bulk liquid to the surface of the boundary layer. Step 2 is the diffusion through the boundary layer, and step 3 will be diffusion of the substrate to the active site inside the inert support where the enzyme has been immobilized. So now please note step 1 and step 2 here, they come under external mass transfer resistance. So they will give external mass transfer resistance. Step 3 will have to face internal mass transfer resistance. So now let's characterize the external and the internal mass transfer. So if we have to characterize the external mass transfer resistance, let's assume a case. So an enzyme has been, so let's assume the enzyme has been immobilized on a surface of a solid particle. The path then would only compose of the first and the second step. So the external mass transfer resistance would be come into the picture. The rate of the mass transfer we know is proportional to the driving force. What will be the driving force here? The concentration difference. Now this concentration difference is the concentration difference between the bulk and the surface of the immobilized particle. So your rate of mass transfer, because there is a solid liquid boundary, so depending on the thickness of the boundary, let's assume the resistance is 1 by Ks, because it is a solid liquid boundary. So we will denote the mass transfer coefficient with a subscript S as shown here in equation 1, 3.1. So here, as we have done earlier, your rate of mass transfer of substrates can be defined as Ksa is the surface area of the film, which is the particle, and then Csb is the bulk substrate concentration, and Cs is the concentration at the surface of the immobilized particle where the enzyme has been coated. Now Csb and Cs are substrate concentrations in the bulk of the solution and at the immobilized enzyme surface respectively. So the term Ks is the mass transfer coefficient and A is the surface area of the immobilized enzyme particle. So now rate of mass transfer of the substrate is what is equal to the rate of reaction. So rate of reaction, let's assume, is following Michaelis-Menten kinetics. So ds by dt or dcs by dt can be written as Ksa Csb minus Cs, and then we have used Michaelis-Menten model here, where Rmax is the maximum rate of reaction, Cs is the substrate concentration which has reached the enzymes, Km is the Michaelis-Menten constant, and small a is the total surface area per unit volume of the reaction. So because this is equal to Cs dCs by dt, initially it was mass transfer. This will become equal to dCs by dt because volume can be divided with the mass, and this will become concentration of the substrate, and the numerator volume will go to the RHS where we had Ks A. So that volume will come here and this will become Csb minus Cs. So now A by V here can be written as small a, where V was the volume of the reaction and A was the surface area. So then this equation can be represented as shown here in equation 3.2. So small a is the total surface area per unit volume reaction solution or reaction volume, and this equation then shows the relationship between the substrate concentration in the bulk of the solution and at the surface of the immobilized enzyme. So we have now a relationship between Cs and Csb. Now give it a dimensionless form. We will have the entire equation 3.2 divided by Csb. If we do that and substitute Cs by Csb as Xs, then and also bring some constants together and further break them into some dimensionless entities, which is called as Zamkohler number, which stands for the maximum reaction rate to the maximum mass transfer rate, and beta, which is given as the bulk substrate concentration to the Michaelis-Menten constant. So this dimensionless number, which is called as Damn-Coehler number, it defines the ratio of the maximum reaction rate over the maximum mass transfer rate. So, depending on the value of the Damn-Coehler number, one can make out whether the system will be mass transfer limited or whether the system will be reaction rate limited. So, let us simplify this equation 3.3. So, after you substitute, divide that 3.2 with CSB, then we end up in equation 3.3. Now, using 3.3, let us take some cases. Let us take case 1 where the Damn-Coehler number is found to be very small. Very small Damn-Coehler number, if you go by the definition, would mean what? That the rate of mass transfer is very high than the rate of reaction. So, the slowest step is the governing step. So, which means that mass transfer is much greater than the reaction rate, and therefore, the overall reaction would be controlled by the enzyme reaction rate. So, then reaction rate is given as in the form of Michaelis-Menten equation. So, now because the mass transfer is taking place very fast, so there are no mass transfer limitations. So, then what reaches the surface of the immobilized particle would be equal to the bulk concentration, and then the bulk concentration of the substrate is what is participating in the enzymatic reaction. So, where the enzymatic reaction rate can then be given as equation 3.5. Let us take the second case where the Damn-Coehler number is found to be very high. In that case again, the reaction rate, this means, is much greater than the mass transfer rate, and the overall reaction rate therefore is now being controlled by the rate of mass transfer. Now, in this again, if you see the rate of mass transfer, so the reaction rate is very fast. If the reaction rate is very fast than the rate of mass transfer, so which means by the time as soon as it reaches, it gets consumed in the reaction. So, we can assume that on the surface the substrate concentration is nearly 0. So, your maximum reaction rate or the reaction rate can then be given as KSA multiplied by CSB. Now, this in terms of the bulk substrate concentration is a first order reaction. Now, in order to measure the extent with which the reaction rate is being lowered because of the resistance to mass transfer, another term is defined which is called as effectiveness factor. Now, this effectiveness factor in immobilized systems, the enzymes, can be given as the actual reaction rate to the reaction rate if not diffusion limited. So, in immobilized enzyme systems which are following Michaelis-Menten, this means what? That the efficiency factor, if it is following Michaelis-Menten equation and in actual condition there is some substrate which reaches due to the diffusion limitations, the resistance to the boundary layer, there is a substrate CS which is different from the bulk substrate concentration. So, your reaction rate was given as shown on the numerator. This is the actual reaction rate. Now, if the same system was not diffusion limited, so whatever was the bulk concentration would have reached the surface, very fast mass transfer. So, in that case the reaction rate would have been as shown in the denominator, where the substrate is then concentration is equal to CSB. Now, we again use the dimensionless forms XS and beta, and as shown here on the slide, it will take this form. So, your effectiveness factor has now become a function of XS and beta. Now, if XS is equal to 1, which means what? XS was what? XS was CS by CSB. Now, if XS is equal to 1, which means CS is equal to CSB, the concentration at the surface is equal to the bulk concentration. Now, substituting 1 for XS in this equation, you will see the eta value becomes equal to 1, which means no mass transfer limitations. On the other hand, if excess approaches 0, if it becomes very nearly 0, so then your eta value also becomes equal to 0. In this case, this demonstrates that the rate of mass transfer is very slow as compared to the rate of reaction. The system is mass transfer limited. Now let us talk about internal mass transfer resistance. So if the enzymes are immobilized by copolymerization or by microencapsulation, then the intra-particle mass transfer resistance can affect the rate of enzymatic reaction. Now in order to now characterize this or derive an equation that can show how mass transfer resistance is affecting the effectiveness of this immobilized enzyme, then we start with few assumptions. So the reaction occurs, but what are the assumptions? First, we will assume that the reaction occurs at every position in the immobilized enzyme and the kinetics of the reaction are of the same form as observed for the free enzyme. The second assumption, mass transfer through the immobilized enzyme occurs via molecular diffusion. So we are assuming that the mass transfer in this immobilized structure is only occurring through molecular diffusion process. Third, there is no mass transfer limitation at the outside surface of the immobilized enzyme. And the fourth, for ease, we will assume that the immobilized particle is spherical in nature. So if you see the picture on the slide, there is a spherical biocatalyst inside which the enzyme has been immobilized. It is suspended in the bulk liquid and we will assume that there is no external mass transfer limitation. So the boundary layer is absent, but the photo shown here is an actual scenario where if you make a plot of the concentration of the substrate or any component in the medium versus the R, which is the center of the spherical pellet, is your origin. So what you can observe is that the concentration decreases wherever there is mass transfer limitations. So from the bulk, which is CAB, it goes down because of the boundary layer, the solid liquid boundary layer, and then once it reaches the surface, because of the intra mass transfer resistances, intra-particle, the concentration further goes down, diffusional limitations, before it reaches the center of the spherical particle. Now the spherical particle radii is given as capital R. So this is the substrate concentration profile in a spherical biocatalyst expected in a immobilized system. Now in order to find how the substrate concentration will change from the surface till the inner core, we need to bring the substrate concentration as a function of the radii of the pellet. So how do we do that? We will assume that it is a spherical particle and we will cut out a shell in this spherical particle and we will do a mass balance for the substrate across the shell. Now the model which we will develop under these assumptions will be known as distributed model. Now because outside we assume there is no mass transfer limitation. So first we derive a differential equation which describes the relationship between the substrate with the radial distance in the immobilized enzyme. So if we start doing the material balance for the substrate across the spherical shell, now this spherical shell we will assume has a thickness small dr and small r is the radii from the center at which this shell has been cut of thickness dr and capital R is the radius of the pellet. And we can assume that CSB is the bulk substrate concentration at the surface and CS is the substrate concentration at the surface of the shell. So if you use continuity equation, which means do the material balance, then input minus output plus generation or consumption will be equal to accumulation. Now, in case of a consumption, this will become minus. Now, because it is a substrate, so there would be consumption and not generation. So, if you see the rate of input and the rate of output, we know that it is following diffusion process. So, your Fick's law of diffusion has been used and the rate of input and the rate of output have been placed at the first two terms, and the third term here defines your substrate consumption rate, and on the RHS is your rate of substrate accumulation inside the shell of thickness dr. Now, to understand this better, let us take the half of this spherical shell. So, let us assume here the notations have been deferred. For the ease in understanding, let us assume that this thickness is delta r, small r, and as I said, small r is the radii at which the shell has been kept and capital R is the actual radius of the pellet. So, as shown here, the substrate is diffusing inside this pellet to reach the core. So, now with the Fick's law, input as I am drawing here, then output difference will be equal to the accumulation of the substrate in the shell. So, the rate at which it is coming inside is your first term. The second term, which is again being defined by the Fick's law, is the rate at which the substrate is going out at a distance r, and at a distance r plus r it was coming in. And the third term is your reaction rate in this shell, which is equal to the consumption rate of the substrate. So, now if you put the limit that delta r tends to 0, then putting this limit here, you can bring it in the form of differential and it takes the form of equation given in the end. So, if you see, this becomes equal to differential because you are putting the limits delta r tends to 0 and dAe has been brought out of the bracket because this is the diffusivity constant assumed to be a constant. Ca and R are variables and Ra is your reaction rate. So, again when you take the differential of the entities in the bracket, it will expand as shown here in the last equation. So, now this equation 1 corresponds to equation 3.11, where Rs here is the reaction rate, can be any, can be 0 order reaction, first order reaction kinetics, can have a Michaelis-Menten kinetics. So, what has happened, this equation 1 here has been divided by r square completely. So, if you divide the entire equation by r square, this will become equal to your equation 3.11. So, now in order to solve 3.11 equation shown here, you can substitute a suitable expression for the reaction rate Rs. Now, let us take some cases. Let us first assume a 0 order kinetics. So, for a 0 order kinetics, the rate of substrate consumption is constant with respect to substrate concentration. So, your reaction rate is, let us assume, is minus k naught, where k naught is your reaction constant, rate constant, for any value Cs greater than 0, and if the Cs is not there, then obviously the rate of reaction is 0. So, if you remember your Michaelis-Menten kinetics, which is your V is equals to V max S upon S plus Ks, Km, in this takes the form of a 0 order reaction if your Km value is very less than Cs, which means it has very high affinity for the substrate. Then in that case your K naught will become equal to your maximum reaction rate, which they have represented as Rmax. Now, if we substitute this in your equation 3.11 in place of Rs, then we place here as minus Q naught, and then you divide the entire equation by diffusivity constant dAe here, which is termed as ds here, and this becomes your equation where your Cs is being related to R. So, in order to solve this double differential equation, we make use of the boundary conditions. Now, what are these boundary conditions? The change of substrate with R, this will go to 0 when R becomes equal to some critical value. So, this is the maximum radii till which the substrate is being able to penetrate, beyond which there is no substrate. So, obviously your dScs by dr, the rate of change of substrate with the radii, is nearly equal to 0 when your R tends to be that critical radius. Now, at the surface where R is equal to capital R, your substrate concentration is equal to the bulk substrate concentration, because there are no external mass transfer resistances. So, this forms your boundary condition 2. So, the first one was dCs by dr tending to 0 at R is equal to Rc, and Cs becoming equal to Csp at R is equals to capital R, which is the radius of the pellet. So, now in order to solve this differential equation given as 3.13 with the boundary conditions which we have numbered as 1 and 2, to solve this, if you do a mathematical substitution of a quantity alpha, which is a product of R and Cs, and further use it, you can reduce the earlier equation into a simple double differential form, which you can integrate and then apply the boundary conditions to get the integration constant values, and then come back to the original equation to find a relationship between Cs and R. So, your equation 3.1 where C1 and C2 were integration constants, their value can be obtained using boundary conditions. So, your solution for a zero order kinetics is shown here in terms of your critical radii, your bulk substrate concentration and the radius of the pellet, given the values of the reaction rate constant of zero order kinetics and the diffusivity of the substrate through the pellet. So, now if we want to find out the efficiency, an expression for the efficiency factor for such a system, we can find out the actual reaction rate. So, what is the actual reaction rate? Now, the actual rate here according to the distribution model with zero order kinetics would be nothing but 4 by 3 pi R cube minus Rc cube, which is the effective volume of the pellet, because beyond Rc there is no substrate getting inside. So, effective volume is R minus Rc, 4 by 3 pi R cube is the total volume minus 4 by 3 pi Rc cube, which is the solid pellet in which there is no substrate getting in. This volume multiplied by the reaction rate constant. So, this is your actual reaction rate, the maximum rate possible with no diffusional limitations. So, if there will be no diffusional limitations, then your Rc will become equal to 0. So, then in that case your reaction rate becomes 4 by 3 pi R cube into K naught. So, then your eta, which is your efficiency factor, can be given as a function of the critical radii and the radius of the pellet. So, if we need to get an expression for that critical radii in a zero order kinetics immobilized system, enzymatic system, then we can find an expression by adding the boundary condition that when R becomes, when small r becomes equal to Rc, your Cs becomes equal to 0. So, now let us take another case of a first order kinetics. So, if the rate of substrate consumption is a first order reaction with respect to the substrate concentration, then in a first order kinetics it can be demonstrated by equation shown here as 3.23. So, where K is your rate constant and Cs is the substrate concentration. So, your reaction rate is a function of substrate concentration. Now, putting this in the earlier equation, double differential equation, and using dimensionless entities which we did earlier as Xs and R dot here is a dimensionless form for the radii, where small r by capital R is your R dot, and all the constants have been brought together in the form of Thiele modulus, which has been given as phi. Now, this Thiele modulus takes the form of r by 3 under root k by ds. Now, the physical significance of Thiele modulus, if you can understand from the arrangement of constants here, it seems to be a measure of the reaction rate relative to the diffusion rate in the denominator. Now, if the Thiele modulus is very less or very high, we can find out that whether reaction rate is high or whether diffusion rate is higher. So, Xs is bounded, which means dCs by dr is nearly 0 when your R is 0. So, we are assuming that it is able to reach till the inside. Your Xs is equal to 1, which means Cs becomes equal to the substrate at the surface when your R is equal to capital R. So, it is saying that the substrate concentration is the bulk substrate concentration at the surface of the pellet in terms of your. So, the boundary conditions have been framed in terms of the dimensionless entities. Now, again the same equation, the double differential equation, to solve it we do the substitution in terms of alpha. So, here the alpha dot becomes equal to R dot Xs, so that the double differential equation takes a simpler form for integration, and we will again integrate twice to get the integration constants, and using the boundary conditions we will solve for the integration constants. So, when all this is done, your Xs is related to R, your Xs was nothing but Cs by Csb. So, effectively your substrate concentration is being related, and your R dot was R by R. So, the Cs is indirectly being related to your radii of the pellet. So, this equation 3.3 finally will show how your Cs will change with the radii of the pellet inside the pellet if the reaction kinetics is being governed by a first order reaction rate kinetics. Now, let us see how Thiele modulus affects your profile of substrates versus the radii of the pellet, or how does it affect the substrate profile inside the pellet. So, Xs versus R dot, we have a plot here. Now, there are different phi values given. So, for a very high value, higher the phi value, you will see that R dot, the range is from 0 to 1. It is a dimensionless entity, it is a fraction. R dot was small r by capital R. So, it can change the form from 0 to 1, the range can be from 0 to 1. So, when R dot is equal to 1, which means at the surface. So, when Thiele modulus is very high, and what was Thiele modulus? Thiele modulus was a ratio of the mass transfer to the diffusion rate. So, which means mass transfer rate is higher than the diffusion rate. So, if mass transfer rate is higher than the diffusion rate, the reaction rate is faster than the diffusion rate. So, most of the substrate will be consumed near the particle surface. Now, similarly, if the Thiele modulus value is low, then this would mean that the rate of enzyme reaction is slower in comparison to the diffusion rate.